Alright, let's talk about chapter 6.1, graphs of the sine and cosine functions. So this first thing I want to talk about is periodicity. So a function has periodicity, or is a periodic function, if and only if, for any specific p, some real number, we have that f of x plus p equals f of x for all x in the domain of f. That is, the function repeats after a certain point. This point p is called the period of the function. So that's a lot of words, but a periodic function is just a function that repeats after some point p. So once you get there, it keeps going over and over and over. So that's the first definition. And you can see here that we're going to be talking about graphs of these two functions, the sine and cosine function. And you know four other functions: tangent, cotangent, secant, and cosecant. And they're all made out of just sine and cosine. So if we know the sine and cosine functions, then we know all of trig. So we want to put these on graphs, that is, our input-output graphs that we've been doing for forever, our xy plane, our Cartesian coordinate system, if you will. But before we do that, I want to say one other thing about sine and cosine. So I want to talk about even and odd functions. So recall that an odd function is a function such that f of negative x equals negative f of x for all x. And then an even function is a function so that f of negative x equals f of x. That is, let's give an example of an even and an odd function. So we want the property for even that f of negative x equals f of x, equals f of x. So f of negative x equals f of x. So what function can you think of, this is for even, what function can you think of so that if you plug in a negative, it's the same thing as plugging in a positive? That's what this means. Plugging in a negative value is the same thing as plugging in a positive value. And you may think, well, squared, just the squared function. This is true, right? That's true, and it is true. So the function is square something. That is, in fact, an even function. An odd function has the fact that f of negative x equals negative f of positive x. That is, plugging in a negative on the inside is the same thing as just pulling that negative out. That's what negative means in terms of odd. So even and odd, that is the parity of a function, whether a function is even or odd, has to do with what happens to negatives if you plug them in. What can you do with negatives? And you can think of an odd, obviously, as a cubic function. If I take a negative x, and plug it into a cubic function, it equals the same thing as just negative x cubed. If you don't believe me, negative x cubed is just negative x times negative x times negative x. And of course, this negative times this negative is plus a positive. X times x times x is x cubed, but you still have that negative here left over, which is where all that comes from. So that is an odd function, and you may notice that 3 is an odd number and 2 is an even number, and that's actually kind of where even and odd came from, as far as my research has told me. So that's even, that's odd. And these functions are what we're talking about. So we're going to actually define even and odd for sine and cosine in just a moment. Just keep in mind that that's what it means. Odd means you can pull the negative out. Even means that it just ignores the negative, basically. Squaring negative x is the same thing as squaring x. It just ignores the negative. However, cubing negative x gives you negative x cubed. You pull it out, so there's still one remaining. Just keep that in mind when we move on. So here's some characteristics of the sine and cosine functions, absolutely worth writing down. The sine and cosine functions have the following characteristics, and don't let me just spit a bunch of math at you and you just put it in your head and try to remember it. I'm saying this ahead of time so that you can have it written down, so that as I'm doing the next few examples, you can look back at this and verify for yourself that these are all true things and that these are all true statements. And if you get to the end of this video and you go back and you read this and you don't know what any of these four statements mean, it means that you didn't get everything that you needed out of this video. And this is the first of the real useful bits of trigonometry that we get to. So far we've just defined these functions. Now we're actually going to start marrying it back to math analysis, which is the whole point of this entire chapter, chapter 6. So let's talk about the sine and cosine functions. They have the following characteristics. They are periodic functions with a period of 2 pi. Now we just defined period, and it means that they repeat after p. So p here must be 2 pi. So capital P must be 2 pi. So after 2 pi, they start doing their thing over again. So we know that the graph is going to repeat over and over. Every 2 pi, if you take a section that is 2 pi long and copy and paste it over and over, that's what this function is going to look like. So that already should look pretty interesting because we don't have any other functions that do that yet. Their domains are each negative infinity to infinity, that is all real numbers, and their ranges are each negative 1 to 1. Okay, so you can plug in anything to them, but the biggest they ever get is positive 1, and the smallest they ever get is negative 1. Because remember that domains are your inputs, and this is something worth remembering, inputs, and your ranges are your outputs. And that's actually how we're going to think about the graph here in a minute. So our outputs are negative 1 to 1. We're going to keep repeating every 2 pi, but we can put in anything, which means that it's going to be defined everywhere. Okay? The graph of f of theta equals sine theta is symmetric about the origin. Okay? We'll get back to that in a second. And it's an odd function. Okay, so we know right now that sine theta is odd. So let's note that down, and let's go back and remember what that meant. So remember, I'm going to erase this. You don't need to write it, but odd meant odd behaves like this guy does. How does this guy behave? Think about it. Well, this is just this in the end, right? That's how odd behaves. So odd behaves such that you can bring the negative out. So that must mean then that the sine of negative theta equals negative the sine of theta. It must behave exactly like that cubic guy did. So that's worth thinking about. And we also said that it's symmetric about the origin. You know something that's symmetric about the origin. It's an odd function. Look at x cubed, for example. X cubed is symmetric about the origin. Symmetric about the origin means it's symmetric about the line y equals x. So this is x cubed. This is symmetric about the origin. This is symmetric about the origin, this guy right here. What that means is that you can fold it, you can fold it over itself both ways. So basically you fold this paper up into fourths and they would be hitting on each other. That is, you can fold it over this line. So you see, if you fold this over that line diagonally, it will be touching. That is symmetric about the origin, is what we're talking about. So the idea is as you fold this, it's actually two folds. It's a fold downwards and then over. So if you think about it that way, it would all be there. So if you fold downwards and then over, like I showed you, this quadrant will be locked, and it'll fold down and over. That's what we mean. Usually when you talk about symmetric about the origin, you talk about symmetric with respect to this line. Which means if you flip it over this line, it'll be an inverse of its. Don't worry about it. But that's symmetric about the origin. Cosine is symmetric about the y-axis. It's an even function. So we know that cosine of theta is even. And I'm going to do the same thing here. So cosine is even must mean that it behaves like this guy. This guy's even, x squared. It's the easiest even function we remember. What happens to the negative? Well, it just goes away, right? So this must mean that f of negative x equals f of x for all x. Well, that's useful. So then our property that we're going to write down for this is that the cosine of negative theta must just be the cosine of theta. That is, cosine doesn't care about negative signs on the inside. Doesn't matter. So cosine of negative pi over 6 and cosine of pi over 6 should be the same number. And if you don't believe me, go look them up on the unit circle. It should be in your head. And then let's think about a function. This isn't what cosine looks like, but let's think about a function that's even. We just use x squared. Let's just use x squared. X squared looks like this. And if it's drawn symmetrically, this is symmetric about the y-axis. If you fold over the y-axis, it's pretty easy to see that these things will hit on each other. So keep all of that in mind as we go about it. And you need to know at the end of this what a period is, the domains and ranges of each of these functions, their symmetries, and whether they're even or odd. And it should be easy enough to remember a bunch of that stuff. But some of that is stuff that just goes in your head. Sine's odd, cosine's even. You want an easy way to remember that? I don't know if there is an easy way to remember that. I just remember that cosine and its brother secant, its reciprocal, secant, are both even. Everything else is odd is the easiest way to remember it for me. But if you insist, look here, cosine is even, sine is odd, right? C comes before S in the alphabet, so too does E come before O. It's however you want to remember it. This is mathematics. It's an advanced mathematics class. Either I'll leave it to you to find some patterns in this to help yourself remember this. But this is all stuff that you should absolutely know that is only going to aid you in the future. Let's move on. So the graph here asks us to use a table to graph the function f of theta equals sine theta for, and what this means is theta in the range of 0 to 2 pi. So we're going to start at 0. We're going to start here. We're going to start here. And we're going to end here. That's what that means. So that's theta in the interval from 0 to 2 pi. Another way to write this that you may see written, notice that they're both brackets, so we include both, is this. This would be another way to write this. You see this all the time. This is read theta between 0 and 2 pi. Inclusive, if you want to use the word that tells you that you use both 2 pi and 0. Inclusive means both of them. So we want to use a table to graph the function sine theta. So let's do that. So here is a place for us to do this. Remember that we're wanting to do f of theta equals, this is the graph for sine. Okay, so let's think about this carefully. This is, the input is theta. The output is f of theta. So let's go ahead and label our axes first off. So let's label this to be the theta axis. And let's label this to be the f of theta axis. Be careful about using x's and y's here. That may get a little confusing. And we can do this pretty simply because we know values of theta. We know a bunch of cool values for theta, and we know what sine is when we plug them in. So let's go through and think about that. So over here, we're going to make ourselves a little table, and we're going to call this theta and sine theta. That is what you get in after you get out. And I want to do it for everything between 0 and 2 pi. Now, I'm only going to do it for the first few, just to sort of give you a general sense of the shape. But I can actually show you a much bigger pattern if you want to go plot it all. So we want to start with 0. That's what it said. Because this was f of theta equals sine theta on 0 to 2 pi, on the interval from 0 to 2 pi. So we want to start with 0. And then let's count up by pi over 4s, because those are the easy ones. Those are the easy ones to do. So pi over 4, and then 2 pi over 4, and then 3 pi over 4, and then 4 pi over 4, which is just pi. Okay, we're halfway there. 5 pi over 4, 6 pi over 4, I'm just reducing these, 7 pi over 4, and this one actually wants us to include 2 pi, so let's include 2 pi. And then let's ask ourselves, what are the values? And I'll do them in orange here. What are the values? So the sine of 0. So go look on your unit circle. So remember, the sine of 0 is the y's. These are the y values. Do not get the y values confused with this normally being the y-axis. It's not. It's the f of theta axis. Keep that in your head. It's just the output of the sine function. This is the output. This whole axis is the input. Just keep that in your head. Don't let that be confusing, or cosine's going to blow your mind. But what is the sine of 0? If you look, the sine of 0 is the height when you're on the unit circle, and you'll notice that that is very much assuredly 0. The sine of pi over 4, we're just looking at the y-coordinates going around the entire unit circle every 45 degrees, basically. So it'll be root 2 over 2. Okay, 1, root 2 over 2, sine of pi is 0, and then negative root 2 over 2. negative 1 for sine of 3 pi over 2, negative root 2 over 2 again for 7 pi over 4, and then for 2 pi we're back to 0 again. So here are the coordinates that I'm going to put up. I'm going to do the coordinate 0, 0, the coordinate pi over 4, root 2 over 2, the coordinate 1/2, 1, the coordinate 3 pi over 4, root 2 over 2. Because remember, what these things are is theta, so that's your x-coordinate, and then your y-coordinate is f of theta, which f of theta was sine of theta. So that's just this. That's your y-coordinate. Your, in huge quotes, y-coordinate. Remember, it's just the output. So let's do that. 0, 0. That's the easy one. So 0, 0, right there. Right? I'll check them off as I do them. Pi over 4, root 2 over 2. Now, look at how I've labeled the theta axis here. I've labeled it in terms of pi's, just to make this easy. This is how we normally do things. So you'll notice that pi over 4 is halfway between 0 and pi over 2. It's why I chose it. So here's pi over 4. And then we need to do root 2 over 2. And you can believe me or not, but root 2 is slightly larger than 1. So then this number should be slightly larger than 1 over 2. Root 2 over 2 is slightly larger than 1 over 2. Root 2 over 2 is probably about here, I would reckon. So let's try to do that. Let's go ahead and do root 2 over 2, since we need it a lot. And then let's come down here the same distance, and do negative root 2 over 2. So there we go. At pi over 2, we are at 1. So we did that one. We did at pi over 2, we're at 1. At 3 pi over 4, which I reckon is about right here. So I'm going to label it 3 pi over 4. Because remember, this could have just been 2 pi over 4. Right? This could have just been 4 pi over 4 instead if we wanted to count all the way up, but we don't. So at 3 pi over 4, we're back down to root 2 over 2. So I'm just going to come right here and sort of eyeball that right here. Is root 2 over 2. And then we did that. Now at pi, we're going to have 0. So at pi, we're going to have 0 again. So at pi, we had 0 again. So I went ahead and did that one. 5 pi over 4 is negative root 2 over 2, which I've already labeled. So here's negative root 2 over 2 at 5 pi over 4. We're at negative 1 at 3 pi over 2. At 7 pi over 4, we're back at negative root 2 over 2 again. So here's 7 pi over 4. We're back up here again. And then we're at 2 pi here at the very end. And we're done. So now all that remains to do to actually graph this is just, well, graph it. And I'll do it in green here. So if I very carefully, which is difficult to do on this tablet, but if I very carefully come through and do this, you'll notice the overall pattern looks something like this. Which you may notice that pattern to be what's called a sine wave. This is called a sine wave. And if you've ever looked into sound, how sound works, or if you've ever looked at electricity or magnetism or pretty much anything in physics, literally everything is just a wave is a popular form of string theory, is a popular form of a way of explaining the universe. So this is what you are. You're just a bunch of these things vibrating around is what string theory says, if you buy into it. I do, but that's up to you. This is a sine wave, and it's just one period. You could see pretty clearly, if you kept going on this list, after 2 pi, 8 pi over 4 would be 9 pi over 4. But of course, 9 pi over 4, you're just back here again. 9 pi over 4 is just the same thing as pi over 4, except you went all the way around the circle, and then you went back pi over 4 again. So 9 pi over 4 is going to be root 2 over 2. And you can see that 10 pi over 4, or 5 pi over 2, which is the next thing, 5 pi over 2 rather, is just the same thing as pi over 2. It's just going to be 1. And it's just going to keep repeating and repeating and repeating and repeating on and on and on and on. So you can imagine that what this thing's going to do is it's just going to keep doing this forever off the screen. And if you go back this way, in fact, it'll do that again if you want to draw the other thing. Now this doesn't need to go in your notes, But you're welcome to like dot that if you want to. Dot this part over here if you want to show yourself that yes, that is what it does. It'll just repeat. And that's why that's called a period. So between right here and right here is one period of the sine function. And you can copy and paste that and keep doing it forever in the other direction, spacing it out evenly, and that will be what the entire function look like, is every single period. It'll just keep going up and down and up and down and up and down forever. That's what the sine function is going to look like. So keep that in mind. Also, notice that you can choose any period of 2 pi. Like from right here, for example, from negative pi over 2 to 3 pi over 2, if you copied and pasted that forever, it would create the same shape in both directions. It'll join up seamlessly down here at either end, and it'll keep going that way for forever and that way for forever if you keep copying and pasting it and joining them at the ends. Any amount of 2 pi will do it. By the way, the distance between 3 pi over 2 and negative pi over 2 is given by the further right distance minus the further left distance, which you might notice is just 2 pi, the period of the sine function. That's how you get this distance, is you take this here minus this here. So no matter what you do, no matter which two of these you choose, you could say, for instance, go between negative pi and positive pi, and that's still 2 pi. Pi minus negative pi is obviously 2 pi. And if you take that section of the graph that goes in this box right here, that goes in this box right here, and you copy and paste it over and over and over again, you can see that this part would quarantine with this part, and we keep going, correspond with that. That going down here would be that going down here when you copy and paste it left and right over and over. So that's why we say that the period is 2 pi. Think of the period as this box, and you can slide this box left or right anywhere along the x-axis. And as long as the box stays at 2 pi, that's what we said, some fixed p, as long as it slides, that is going to be one section, and the entire section, that if you copy and paste that section, no matter what section's in the box, left and right forever, they'll join up nicely, and it'll make that nice sine wave. That is a sine wave. Now we're going to go on and draw the cosine, and we're going to notice that it's not any more difficult. So this thing asks us to do the exact same thing. It says graph cosine for 0 to 2 pi. And I urge you, using what we did on sine, go ahead and graph sine. Go ahead and graph cosine. Just remember, cosine is the x inputs. But go ahead and graph cosine. Give it a shot. Draw out your axis, just like we did in the last problem, and go ahead and give that a shot. Go ahead and pause the video and see what you can do. So hopefully you listened to me. But if you didn't, that's fine. Just try and pay attention here, and we'll figure out what's going on. So this is f of theta. Let's do it in a different color. Let's do it in orange this time. So let's do f of theta equals the cosine of theta on 0 to 2 pi is what we want. So cosine. So this is your f of theta. This is cosine. And this is your theta. Now, cosine is normally the x value from the unit circle. But remember that cosine theta is the output here. So this is actually x equals f of theta here, and this is theta, your input. Remember, what I said was, think about this in terms of your input and then your output. And remember, what these functions, cosine and sine, give you are the corresponding x and y coordinates on the unit circle, respectively. Cosine gives x, sine gives y. So the output of cosine is always going to be the x coordinate from the circle. So what this is going to end up being when we graph this whole thing, and let me move theta over here. When we graph this whole thing, it's going to end up being the x coordinates graphed. And you can graph every single one of them if you want to, but I'm going to do it the same way I did it last time. So here's theta, and here's cosine theta, and we're just going to graph the main ones. So 0, we're going to do pi over 4, we're going to do pi over 2, 3 pi over 4, we're going to do pi, we're going to do 5 pi over 4, we're going to do 3 pi over 2, We're going to do a couple more. We're going to do 7 pi over 4, and we're going to do 2 pi. And keep in mind that these are just the 45-degree angles. I chose them because they're easy. You could have done all the 30-degree angles as well, or just the 30-degree angles instead, along with your quadrantial angles. So you could have done 0, pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, so on and so forth, just reducing those numbers, and you would have got the exact same graph. You would have actually had more numbers on it. It doesn't matter which one you do. The point is you just have to have enough numbers to do it. The big points are the quadrantial ones, 0, pi over 2, pi, and 3 pi over 2, and I guess 2 pi too, because it's the same thing as 0. So the quadrantial angles, that is the ones that occur on the unit circle, not on this graph, but on the unit circle here, 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 and here. Think about the unit circle, not this graph again. Those are the quadrantial angles that I'm talking about. So 0, 90, 180, 270, 360. So let's go ahead and go through and do these again. So cosine is the x coordinate this time. So cosine of 0 is 1. The first coordinate is 1, 0 over here on the unit circle, not on this graph. This graph is labeled different. This graph is a theta, f of theta graph. Your unit circle is an x, y graph. Please keep that in mind. Pi over 4, so it's going to start getting shorter, but still be positive. So it'll be your root 2 over 2. At pi over 2, we're at 0. At 3 pi over 4, we're at negative root 2 over 2. At pi, we're at negative 1. At 5 pi over 4, we remain at, we go back to negative root 2 over 2. At 3 pi over 2, we're back to 0 again. Then we go to positive root 2 over 2, and then we go to 1 again. So that's what our cosine is going to look at. And remember that this is just your x values. So just go look up your x values for all your thetas on your unit circle, and you'll see that that's what it is. So now on this, where this is the theta axis and this is the f of theta axis, I keep mentioning it because it's important, we're going to actually plot all of these points. So let's plot all these points. So at 0, we're at 1. So we start up here for cosine, apparently, and then we go down. So root 2 over 2 is about right here. Negative root 2 over 2 is about right here. So root 2 over 2. It's just above. I think right there is 1/2. I go a little bit above it. I put it basically at 3/4. I mean, it's not at 3/4, but I put it basically at 3/4. That's close enough to sketch it. I don't know why I erased that. Root 2 over 2. This is negative root 2 over 2. So let's go ahead and do that. So remember, let's go ahead and label the rest of these as well. So that's pi over 4. Remember, we could have labeled this 2 pi over 4 if we wanted to. But we didn't label it 2 pi over 4. We labeled it pi over 2. We reduced it. So then this is 3 pi over 4. And then 4 pi over 4 goes right here, but that's just pi. 5 pi over 4 is the next one. Then 6 pi over 4 goes right here, but 6 over 4 is just 3 over 2, so we don't write it. And then 7 pi over 4. I get students asking me every year how I keep getting these numbers over and over, and I'm just counting by pi over 4. Literally 0, 1, 2, 3, 4, 5, 6, 7, 8 pi over 4 for each one of these. But you just reduce the fractions that I just erased. So let's go through and go ahead and plot the rest of these. So pi over 4, so we plotted that one. Pi over 4 root 2 over 2 goes right here. Pi over 2, 0 is the next one. Okay, 3 pi over 4 negative root 2 over 2 goes right here. Pi negative 1. At 5 pi over 4, we've come back up to negative pi over, negative root 2 over 2, rather. At 3 pi over 2, we're back up to 0 again. At 7 pi over 4, we're at root 2 over 2 again. And then at 2 pi, we're back up to 1. So look back at your sheet as I fill this out, and you'll notice, I'm going to do this in red. I'm going to try to fill this out as smoothly as I can. It's a nice, smooth curve that never goes below negative 1. So let me do that again. It's a nice, smooth curve that levels off and then goes up through these points and then kind of like that. Yep. That is our boy cosine of theta. So cosine theta goes through these points at these points. And you can see that this is just, again, this is just one period. I said that the period was 2 pi, so this is just one period. So you can imagine if I wanted to come along with, say, this orange line here and extend this, that this thing would look something like this if I just extended it. So it would just continue going. It would be back down to here, and then it comes up, and then it comes back through. And you would see overall that this thing does have that same sine wavy sort of thing. This thing is called a cosine wave. And you may notice that if you just start back here and you go to right here, 2 pi over 2, if you look just between those two giant orange lines and you look at that, it is the sine function. Because remember, the cosine function is just the sine function, but shifted pi over 2. So keep that in mind. That's also reflected. We'll get to that. But it's just a phase-shifted version of the sine function, and we'll get to what that means. That was one of the identities that we had, a cofunction identity that we had from the last section. But it's just the cosine and sine functions are very, very related to one another. That was just something interesting I wanted to bring up. But that is the cosine function. So the cosine function starts at 0, and then you just remember basically these main points that I circled over here. 0, pi over 2, negative pi, 3 pi over 2, and 2 pi. It starts here, and then goes down and hits, goes all the way down to -1, comes all the way back up, and then hits. And that's the quick way that I would sketch that, like I ended up sketching it over here. Just keep all of that in mind as we go through and do this. And what I urge you to do is get out a piece of paper, label yourselves some axes, and draw this thing a whole bunch. It should be in your head. But the real question is, where does this thing come from? So I want to show you an image that goes over this and shows you better than I ever could what's going on. So I'm going to go ahead and give you a full-on cornea alert. If you're watching this in a dark room, I'm about to blow your eyes out. But otherwise, take a look at this. So let's take a look at this. Here I have the sine of theta graphed on the right, and on the left I have the unit circle. So I have this little slider down here, and as I slide this slider, what I'm going to do is I'm going to increase the multiple of pi. So on the left, look only at the left now, as I go ahead and take this thing all the way up to 2 pi. So I'm just going to increase that angle all the way around to 2 pi. So you saw in the middle, watch the angle theta grow in the middle of the circle as I go all the way up to 2 pi, 1 revolution. Then I spin it back. Now, if you keep an eye on the height, that is the red bar on the left, what the sine function is a tracing of that height. So you see in the middle here, this bridge showing you where this comes from. This height over here on the left at the purple dot is the same thing as the height on the right. Think of the sine function being traced. So we get up to our highest we ever are on the unit circle at 90 degrees. Therefore, our function only goes to +1. And then between pi over 2 and pi, the sine function, which is y, comes down. So at pi, here we are, back at 0. We continue height-wise to go lower, all the way up until 270 degrees, or 1.5 pi, or 3.5, or 3 pi over 2. And then we continue onward back to 0 again. So if you want to think about why this thing has a periodicity to it, is a periodic function, you could just continue spinning around again. So think about it, 360, and then think about starting over again. So we've already spun 360, so just do it again. And it traces the exact same thing out. Do it again, it traces the exact same thing out. Do it again, it traces the exact same thing out over and over and over and over, and you just keep tracing over the circle. So that's the sine function. That's y. Okay? Now let's look at x, cosine. So we start at 1 because we're dealing with the x's here. And as I spin around further, the x pans back and forth from left to right. That is, our x's for cosine are getting shallower and shallower and shallower and shallower. And then they're increasing again, and then they come back around. Now, I've seen some versions of this, and you're more than welcome to go look them up. There's some versions of this that'll show this to you with the x coordinate explained up top, like going up and down. I find that to be very confusing for the first person that's ever seen it. You may notice, let me just go to some arbitrary point here in the middle, that we're coming all the way across and then going at this right angle and coming down and looking at it. And why is that we're doing that? Well, remember with the sine function, the height of the graph itself, the sine graph's height on the right, and the height of the height above the unit circle, above the x-axis on the unit circle, were actually both the same height. But for the cosine, there's that switch. On the left, we're talking about x distances. On the right, we're talking about heights, as in y distances. We're actually just talking about outputs on the right versus heights on the left. Don't overthink that. The reason that it ends up looking like this is very simple. We just have to do a little bit of changing for this to end up looking, but that's what it is. Remember, what we're doing is we're taking the output of this, which was the x coordinate over here, and we're changing it into a y coordinate over here. That's why that change of x to y happens. That's literally what this bend is. It's a change of x coming out along straight to y, vertical. Has to happen in order for this to make sense, for this graphic to make sense at least. But the coordinate itself being positive over here, it makes sense because the x-coordinate here is positive. You can see this distance here is about, 1.77 pi radians around is about whatever the cosine of 319 degrees is. It tells you it's about 0.75. It's about 3/4. We're getting close to that. So you can look at this and see very clearly that if you come trace that point over, after you've spun around 1.77 pi, that's this point right here, you go up that distance of 0.75, that's what that point is. And you can see all of these points along here. And then this applet will also do both of them at the same time, and you can see everything. So you see all of these right triangles. If you stop at any point along this, the purple's going to be your hypotenuse, and that there will be a triangle of some sort, with the purple as your hypotenuse, and there being a right angle somewhere. These will all be right triangles. There's a whole host of them. Stop this anywhere. Literally just pause this video anywhere you want to, and there will be a triangle somewhere on this that you're dealing with. Which is why we went through all that right triangle trick, because it's going to come in useful. So I hope that helped. I really genuinely do. I was never shown this. The sine is pretty intuitive to me because they directly correspond to one another because they're both dealing with heights on their respective graphs. The cosine can be a little confusing, but just remember that we're turning what this over here is doing is it's looking up the x coordinate and displaying it as a height over here. That is, we're changing an x into a y. That's why we have to do the bend. If that isn't a good enough justification for you, I'm sure that there may be better justifications for you personally out there. However, that's enough for me. I just want to look at one more thing. And that one more thing is the general form of the sine and cosine function. So let a, b, c, and d all be real numbers so that a isn't 0. The general form of the sine function is a sine b theta minus c plus d. And that should look normal to you. In fact, if I came in here and I put in a g of theta, since theta was our variable, that should look like something that came straight out of math analysis, 1.5 in math analysis. But we've renamed some things. Because these things are special and they show up everywhere, they ended up getting names from physicists instead of mathematicians. So the absolute value of a is the amplitude, or its height. And when we say absolute value, what we mean is that the amplitude is always positive. B is related to the period, but that's not the period. The period will always be given to you by this formula, which is worthwhile to remember. P equals 2 pi over B, absolute value of B. So the period is always positive as well. C and D behave as expected. D shifts the graph up and down, and the phase shift ends up being given by C over B. That is how far left or right we've done this. That's because you can factor this as A times the sine of... Basically, you could pull a B out of this on the inside. And if you pull a B out of B theta, you're left with theta. But if you pull a B out of just C, you're left with C over B, like this, plus D. This form is the form that we normally use in terms of helping us with processing what a sine and cosine function is doing exactly. So this is where this comes from. And if you don't believe me that that would work, just distribute this B back in, and you'll see that you do indeed get exactly this. Anyway, that's where all this comes from. So let's try and remember that the C and D behave as expected. D is going to shift the graph up and down, and then left and right is moved by this factor of C over B. And then note that the same facts are true for the cosine function. So if you want to write all these again for the cosine function, it's true. It's the exact same thing, except instead of writing sine here, you just write cosine. And it's all the same stuff. Sine and cosine behave the same way. And you can think about it for just a second, and it should make sense to you that they behave the same way. Because they're functions, first of all, so they should move around the same way, but sine and cosine are basically the same function. I mean, they look almost identical. One is just moved slightly to the left or slightly to the right, depending on which one you're thinking about, but they look like the same function. They both look like that. I mean, perfectly symmetrical, but they both look like that. That's the sine function, or the cosine function. So I want to look at this next example, and it says state the amplitude, period, and phase shift of the function given to us as f of theta equals negative 2 sine 4 theta minus 2 plus 1. So I want to get those things out, the amplitude, the period, and the phase shift. So let's look at all this, and let's figure out what all that is and what all that means. And then we're done. I want to leave all that up there. We don't need that much space. So we want the amplitude first. So the amplitude is always, take the number in front, and that's the amplitude. So the amplitude is the absolute value of A, which in this case is the absolute value of negative 2, which is 2. So the amplitude is 2. What that means is that this function is going to go, instead of going between negative 1 and 1, it's going to go between negative 2 and 2. If you think about it in terms of sound waves, it's how loud this thing gets. And we'll get more into applications in class. Period. You might be tempted to say that the period is 4, but the period is not 4. The period, remember, is how long it takes to repeat itself. But the period is always given to you by P equals 2 pi over the absolute value of B, where B is the thing in front of the theta. So then this is 2 pi over the absolute value of 4, which is 2 pi over 4, which is just pi over 2. So the period is pi over 2, which means that this sine function does its entire business. It goes all the way up to negative 1, all the way back down to negative 1, and returns to 0. And it does all of that in the space of pi over 2. And then it begins repeating itself over and over and over, which must mean that this is a fast sine wave. It goes up and down real quick. And we'll look at some of these in Desmos in class as well, on a slider. There's a cool little thing that I have for us to do with that. All right. But the last thing that I wanted to do here was phase shift. So let's do phase shift. So phase shift. Phase shift. Okay. The phase shift is always just going to be C over V. Now remember, and try and be careful with this, the normal version of this has a minus in it, which means that your C in this case is positive. So it's 2 over 4. So your phase shift, which I'll call PS, is 2 over 4 or 1/2, which means that this thing has been shifted 1/2 of a unit. In which direction? look back at 1.5. I'll let you do a little bit of a review real quick. But it is a positive 1/2, so you tell me which direction you think it moves. Remember, everything that I pulled from this was inside the parenthesis, so it's the opposite of how you would hope it would move. But that's it for this section. Join me again on the next video, and we'll go over the other 4 functions and their graphs. They get a lot more spicy than this. They look a lot weirder, and they're a lot harder to remember, kind of. But they end up being very easy to remember if you can remember the sine and the cosine graphs. I cannot stress to you enough how important it is that you take the sine and the cosine graphs and you commit them to memory. That being said, we are done here. I'll see you in the next one.